So continuing talking about exponential functions, which we talked about how to evaluate and graph in the last class, some of the most useful exponential functions are growth and decay models. So by the time we're done here, we should be able to model these growth and decay situations and determine amounts that are left after something has had time to grow or decay or increase or decrease. We need to make that determination first off. Before we get into specifically recognizing and using these models, we need to understand what they look like and what the different parts are. So for an exponential growth model, this is a situation where something is going to increase by a certain percentage consistently, right? Or something's going to, one of the problems we saw from our last set of notes was bacteria doubles every, the bacteria population will double every hour or every day or every however long. And so that's a situation where we're talking about some exponential growth. If something is going to grow at a particular rate and will be the same over an amount of time, then we're talking about exponential growth. Now, an exponential growth model will look like this, okay? Y equals a times 1 plus r to the x power. So it's an exponential function because the x is an exponent, right there. And so here are the different parts. A needs to be the amount that we start with. And we're going to have to start with some kind of amount, right? A can't be 0. Going back to the bacteria situation from the last set of notes, if we have 0 bacteria, then bacteria can't grow. So obviously A is going to have to be some value bigger than 0. This part right here, 1 plus r, is known as the growth factor. That's how much, that needs to be our rate by how much something's going to grow or increase or anything like that. Where r is our rate, it's our rate of growth. If it doubles, then r would be 2. Or if it's a percentage growth, then r is going to be, it needs to be the decimal version of that percentage. And then x is the amount of time. How long is this going to be growing before we're done evaluating it? Okay? And so you see down here, for exponential growth, and you probably need to write this in, for exponential growth, the growth factor will be greater than 1. Okay? And that hopefully will make some sense. We're going to take some rate, some decimal, some r, and add it to 1, so the growth factor will be greater than 1. 1 plus % rate of change is a decimal. Okay? Now contrast that, compare and contrast that with exponential decay. Decay meaning something's decreasing, something is going down, or something of that nature. An exponential decay model looks a whole lot like an exponential growth model, right, where it's still y equals a times what's called a decay factor raised to the x power, so it's still an exponential function. A is still going to be the initial amount. X is still going to be the amount of time it's decaying. And r is still going to be the rate at which it's decaying. The difference is this guy right here. In a decay model, we're going to use a minus. We're going to subtract r from 1. Whereas in a growth model, we're going to add 1 to r, or r to 1. Okay? That's our only real difference. And when we do that, for exponential decay, the decay factor ends up being less than 1. And that hopefully makes a lot of sense. Right? If you start with 1, like we're doing here, and subtracting r from it, then it should be less than 1. Now r is still going to be a % written as a decimal, so it won't be negative, it'll just be less than 1. It'll be basically a fraction. Okay? So let's take a look at some situations and try to figure out if these are growth or decay models, or something that would need a growth or a decay model. For example, the value of a car 2 years after purchase. Right? So what would happen to the value of a car 2 years after purchase? Well, you're never going to pay more for a 10-year-old car than you would have paid if it were brand new. So this would be a decay situation, right? What about the interest earned on your savings account? Hopefully you're saying growth. This is going to be a growth situation, because if I'm putting money in the bank in an account that's going to earn interest, it better grow, right, instead of decay. What about C here? What about the third one? Is this going to be a growth or a decay model? If you look back in your notes, this is your factor. Since it's less than 1, this is a decay model. Okay. What about a decline in enrollment at a summer camp? Right? Since we're declining, then this should be decay. Okay, the value of an antique table after 10 years. Furniture is one of those things where it can actually appreciate in value after time, so this is going to be a growth model. And then if you look at this guy right here, here's your factor. The base on your exponent is your factor, and since that factor is bigger than 1, then this is a growth model. Okay? All right. Now that we can tell the difference, hopefully we can, well, let's talk about how to use this function. Okay? In 2005, the amount of money spent at restaurants in the U.S. has increased about 7% each year. In 2005, about $360 billion was spent at restaurants. If the trend continues, about how much will be spent at restaurants in 2015? All right, well, first and foremost, we've got to understand if this is growth or decay. And since it's talking about an increase in the amount of money spent, then this would be a growth situation, right? So, which function are we going to use? Are we going to use the one with the plus or the minus in it? Right? And hopefully you're thinking to yourself, well, we're going to use the one with the plus in it. So, y equals a times 1 plus r to the x power. Okay? Where y is the annual amount spent at restaurants, x is the number of years since 2005, a is the initial amount spent, and r is the rate. So, annual amount spent at restaurants, that's what we're trying to find, right? So we're not going to plug anything in for y. A is the initial amount spent. How much were we talking about initially? And that's here, the $360 billion. Now I'm going to write 360 and just understand that my answer I know is going to be in billions. Okay? Let's see. Number of years since 2005. Well, it's 2015 now, so we're talking about 10 years. So our x is going to be 10. And then r is the rate. How quickly is this increasing? And it's 7%, so it's going to be 0.07 that we're going to put in for r. Okay? All right, now we've got to just multiply all this stuff out, do the arithmetic. First things first, we've got to add inside our parentheses 1.07. And then raise that to the 10th power. Okay, so we've got to do 1.07 to the 10th power. Okay, and we got to know how to do that in your calculator. And so you may need to figure that out based on the calculator that you have. There are different ways that you can put in 1.07 to the 10th power. Okay, when you do that, you're going to get 1.97 basically. But don't clear that out and type in 1.97. Leave that number in your calculator. Now just hit times 360, and it will bring that answer down, the decimal down, and multiply that into 360, and we get 708.17, which means that basically we're going to spend $708 billion at restaurants this year. Okay, about. You can put the squigglies here instead of an equal sign to represent about or approximately. Okay? Make sense? Hopefully. Another one here quickly. The kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000-meter increase in altitude, the pressure decreases about 11.5%. What's the approximate pressure at an altitude of 3,000 meters? Are we talking about a growth or a decay? Right? And since it says decreases, we're talking about a decay. So we need the model y equals a times 1 minus r to the x power, where y is the atmospheric pressure at some point, which is what we're trying to find. A is the initial pressure, x is our altitude, and r is still our rate at which it's going to decrease. Since A is the initial pressure was 101 kilopascals. The rate at which it drops is 11.5%, but we got to put it in as a decimal, so that's 0.115. And then the altitude, it is 3,000 meters, but it says for every 1,000 meters. So how many 1,000 meters is 3,000? Well, it's 3, so x needs to be 3. Okay? So we get, add or subtract the 1 and the 0.115, and we get 0.885. And now we got to raise the 0.885 to the third power. I'll drop my calculator. Okay, and it's basically 0.693, but again, I'm not going to wipe that out of my calculator. I'm going to leave it in there, because now that I've got 0.693 as my result, or actually a bigger decimal than that, I'm going to multiply that by 101 and get a much more accurate result of basically 7.0 kilopascals. Okay, and that's our pressure at 3,000 meters. All right? All right. Try this one. See what you get. Just determine if it's growth or decay, and then plug in the formula and see if what you've done is correct. Stop the video and see what you come up with. Okay, did you get this? Y equals 25,000 times 1 plus 0.015 raised to the 25th power. Okay, that's what you should have gotten. Now we're going to have to just do the arithmetic. Add these together first, so you get 1.015. We're going to have to raise that to the 25th power. And when you do that, you got to take 25,000 and multiply it by 1.45 basically, but again, leave that decimal in your calculator and multiply it by 25,000. And so, the population in 2025 is going to be about 36,273. Okay? Or if you round it up to 36,274. But anyway, this is still an approximation. Okay? So, where 25,000 is your initial population, the 0.015 was the growth rate, and that's why we're doing a growth model here, because it says the population grows. And since from the initial population was in 2000, and they're asking about the population in 2025, our time is going to be 25 years. Okay? All right. Now, how this applies even to finances, right? Putting the money in the bank or earning interest on something. The best type of interest earned is compound interest. When a bank pays interest on both the principal and the interest an account has already earned, the bank is paying compound interest, right? Which means that if you're earning interest at a 3% rate and you put in, let's say, $100, what this means is the first time you're paid interest, it's going to be 3% times $100, or you're going to make $3, okay? The second time you earn interest, it's not going to be on $100 again. If it's compounded, it's going to be on $103. So you multiply that by 0.03 and add that to the 103. Then you're going to take 3% of that and then add that to it. Then take the 3% of that and so on and so forth. That's what we mean by compound interest. Okay? The compound interest is an example of exponential growth. And here's the formula for compound interest. Now here are the different parts, right? A is the final amount, right? That's sort of our Y. A and Y are the same from before. P is our initial investment. How much did we put in to begin with? R is our interest rate. N is the amount of time that we've been earning interest. And T is the amount of time that we've been earning interest. And N is the number of times compounded per year. How many times are you going to get paid out each year? Okay? So, for example, the tough part there depends on how the interest is compounded. Sometimes the interest is compounded annually. If it's compounded annually, how many times are you going to get paid in a year? Well, 1, right? How many times are you going to get paid if it's compounded semi-annually? Well, semi suggests 2. How many times are you going to get paid out if you're compounded quarterly? Well, quarter means 4. And then how many times you can get paid out if it's compounded monthly? That's going to be 12, right? So your N, which is the number of times that your interest is going to get paid out, or how many times it's going to be compounded, your amount, is going to depend on the situation, whether it's compounding annually, semi-annually, quarterly, or monthly. Okay, so let's take a look at an example of this. Suppose when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest, compounded quarterly. What will the account balance be after 18 years? Okay, so here's our formula. A equals P times 1 plus R over N raised to the NT power. Okay, so what does A stand for? A is going to be the balance after 18 years. P is how much we deposited initially. It's our principal. It's our initial amount. R is your rate at which it's earning interest. N is the number of times compounded per year. And T is the number of years that we're going to be earning this interest. Okay? The balance after 18 years is what we don't know. So the A is what we're trying to find. Our initial deposit was $2,000. The rate is 4.5%, which we are going to put in as a decimal. Now, it's earning interest quarterly, so it's getting paid out 4 times a year. And then we're going to look at this, and we want to know how much we have after 18 years. Okay? So, we're going to plug all that in. Okay? 2,000 for P. 4.5% as a decimal for R. 4 goes in for N, both here and here. It goes in for both of those. And the 18 goes in there for T. So what's that going to look like when you do that? This. Okay? So 2,000 times 1 plus 0.045 divided by 4 raised to the 4 times 18th power. So you're going to have to multiply 4 times 18 and get 72. And then you've got to start doing what we were doing before, right? So inside the parentheses, you got to divide the 0.045 by 4 first, add the 1 to it, and then raise that to the 72nd power. When you do that, multiply by 2,000. And you're going to be left with $4,475.53. So after 18 years, your friend will have $4,475.33 in the account. Okay? All right? All right. Try one more together, and then let you take a look at one on your own and see how you do. Michelle invests $8,000 in a money market account that pays 3.25% interest compounded monthly. How much will be in the account after 12 years? We start with our formula. We got to remember that A is the balance after 12 years. That's how long we're going to let it earn interest. P is our initial investment. R is the rate at which we're getting paid our interest. N is the number of times we're going to compound it per year, and T is the number of years. So, balance up to 12 years, we don't know. That's what our A is, right? Our initial investment was $8,000, not ours, Michelle's, right? The rate at which she's earning interest is 3.25%, and again, we're going to put that in as a decimal. And the number of times compounded per year, it's being compounded monthly, so that's going to be 12. The number of years is 12. So, 8,000 goes here for P, 3.25 goes here for R, 12 goes here for N, and that N, and this 12 is in there for T. Okay? What does that look like? This should look like this. A equals 8,000 times quantity, 1 plus 0.0325 over 12 to the 12 times 12th power. Multiply 12 times 12, you get 144. Then we got to do 0.0325 divided by 12, add 1 to that, and raise that to the 144th power. Then you're going to multiply that by 8,000, and when you do, you get this result, which means that Michelle will have $11,809.62 in 12 years with her money market account. Okay? What do you think? I mean, it's really just plugging in a bunch of numbers and doing the arithmetic correctly. All right? All right. Try this one on your own. Stop the video, fill it in, and then do the arithmetic and see if you've gotten it correct. If not, follow along. Start the video, follow along, and fix whatever you did. Okay, so you invest $6,500 at 6.6% compounded monthly. How much money would you have after 2 years? How much interest would you have earned during that time period? So here's an additional question that we're going to have to answer. Figure out how we do that. Okay? All right. Well, first off, here's our formula. Right? A is our balance after 2 years, P is our initial investment, R is our rate, N is our number of times compounded per year, and T is the number of years. Okay, so again, our balance after 2 years is A. Our initial investment this time is $6,500. Our rate that we're getting paid is 6.6%. We're going to compound 12 times in a year, and we're going to do this for 2 years. How much money do we have? Well, when you plug it in, it should all look like this. 6,500 times 1 plus 0.066 over 12 raised to the 12 times 2 power. Okay. 12 times 2 is 24. Now we got to do 0.066 divided by 12. Add 1 to it. Raise that to the 24th power. And then multiply all that by 6,500. And when you do, you get this result. And so that means that after 2 years, you will have earned $7,414.52. Okay? Now, the question is, how much interest would you have earned? Well, out of the $7,414.52, all but $6,500 of it was interest. So, to find the interest, we just take the initial investment out of our total now. So subtract the $6,500 from the $7,414.52. When you do that, you are left with what you're looking at there in the answer, which is $914.52. Okay? That's how you find out how much interest you would have earned. Okay? All right. That's it. So hopefully that makes sense. Homework's out in Canvas. Go out and give it a shot, and we'll talk about it next time.